I want to talk about the displacement field in Gauss's law because we do problems and some stuff that happens that doesn't really think it makes sense. So I'm going to make a more complicated problem. Here's the problem that we could do. Okay, imagine I have a positive charge surrounded by a dielectric sphere, and I want to find the electric field everywhere. Well, the easiest thing to do here is to use the displacement field. So the displacement field, D, we write this as the electric field times epsilon naught plus the polarization. And Gauss's law, if you do that, Gauss's law looks like this. It says that the flux of the displacement field, not the electric field, is equal to just the free charge. Because what's really going to happen is this charge is going to make an electric field, and this electric field is going to polarize this dielectric material, so you'll get a charge density in here, you'll get surface charges, and then you have to deal with all those surface charges and stuff too. But if you use the displacement field, it's pretty easy. Now, here comes the kind of weird thing. Imagine that I choose a Gaussian sphere outside of my dielectric sphere. And I use this. I say, well, what's the displacement field? The displacement field is d dot n hat dA. And if I choose spherically symmetrical stuff, then this d would be q free inside. And the only free charge is this. So let's just write this down. What the heck? I almost tripped. I tripped again. I'm not going to cut that. That's part of real life, right? And this is real life physics. Okay, so if I do that, d is constant over this surface area, and it's in the same direction as r hat. So I get d times the integral of dA is q free. So that's d, and then I can just integrate over the surface area, 4 pi r squared. Q free is just going to be that charge q. Solve for d, and I get q over 4 pi r squared. There's no epsilon naught because it's the displacement field. It's not an electric field. And then I can say, well, now I can use that to find the electric field. So up here, E is going to be D minus P, the polarization, over epsilon naught. Well, outside here, there is no polarization. So I just get E is D over 4 epsilon naught, which is Q 4 pi epsilon naught r squared. I'm then going to add the r hat in because I made that as a vector. But that's the electric field due to a point charge. So what if I took this problem away and I removed the dielectric? I'd get the exact same electric field. And so the question is, did the dielectric field, the dielectric material, do anything? Well, it did, but it didn't. Here's the thing, the kicker, as some people would say. Here's the kicker. If I have this in here and I get a polarization in this material like that, well, there is no extra actual charge, so the free charge is still 0. But because it's all spherically uniform, the spherical distribution of charge is also uniform. And so these polarization dipole moments actually cancel in the spherical case. It doesn't seem like they do, but they do. Okay, and I did a video on that. So let's do a different problem and see if Gauss's law still works. This is still Gauss's law. Okay, so imagine I have the following situation. And we're going to build this, don't worry about that. So here's my positive charge. I'm using colored chalk. I have a positive charge Q. And then I have my dielectric as a block, like that. So that's going to get polarized in some case, like that. And then if I now do Gauss's law as a sphere, well, I still have the total charge inside as Q, but I'd get a different electric field, okay? Because now I have a non-uniform electric field. But what I want to do is to numerically make a charge, make a dielectric material, and then find Gauss's law and show that Gauss's law still works. The sum of the flux around the whole thing is still Q over epsilon naught, but it's not a uniform flux. That's what we're going to do. Now, I am going to use some of my older programs because I don't want to redo my flux calculations. But let's switch over here to Python. We're going to make this in Python. So I already have a start. I have a charge at the origin. All I need to do is to add a block of dielectric. So to do that, I'm just going to make a block of some points. So let's do this. I've done this before. It is kind of fun. So let's just do it. let's say that I have a block of length L, and I'm going to have it shifted over a distance L. Okay. So let's say n is equal to 5. We can start off with 5. We can change it later. And that's going to be 5 by 5 by 5 block, like that. Okay. So I'm going to say ds is L over n. And then I'm going to just start making my points. I'm going to make these points, and then we'll do a bunch of stuff with that. Okay, so I'm going to start a vector position. I'm going to move it in all 3 dimensions and make this cube of stuff. So r start, I'm going to call it rs, is going to be the vector negative L over 2 plus ds over 2, right? So that means I can start in the right spot, which you don't even have to do that. Negative L over 2 plus ds over 2, and then negative L over 2 plus ds over 2. Now I want to shift that over in the x direction, so I'm going to say plus, which you can't see because of my big head, plus vector, let's just say L 0, 0. So now it's going to be shifted over. I don't want it at the origin, although it would work just fine at the origin. But now I'm going to make some loops. So I'm going to say while rs dot z is less than L over 2. I think that works. Yeah. While rs dot y is less than L over 2. While rs dot x is less than L over 2. So I have a triple loop, and at the end of this y loop, I need to reset my y value. So I'm going to say rs dot y equals negative L over 2 plus ds over 2. And then I need to do the same thing here. rs dot x equals negative L over 2 plus s over 2 ds over 2. Plus L, right? Because remember, I'm shifting everything in the x direction. I'm going to have my cube over in the x direction. So that's that. And then over here, I'm just going to make a sphere, and then we can fix it later. So just to say sphere, position is going to be equal to rs. Radius is going to be equal to, let's say, L over 50. That's fine. Now I need to move my rs in the x direction. Rs is rs plus vector ds 0, 0. And then that will be the end of that loop. And then I need to move it in the y direction. So rs equals rs plus vector 0 ds 0. And then I need to move it in the z direction. rs equals rs plus vector 0, 0 ds. Okay, these always scare me, these triple loops, because you get one of them messed up and you get an infinite loop. Maybe a triple infinite loop. Triple infinite loop is worse than an infinite loop, but let's just run it and hope for the best. It didn't work. I didn't even get an error. Maybe my spheres are too small? Huh. Okay, let's just copy. I did this before. L over 2, L over 2, L over 2, radius. What am I doing wrong? Okay, I'm just going to copy this. I'm sure I did something not quite right. It's all right. Okay, let's just copy. You know I worked this stuff out beforehand. There's no magic here, right? So let's just put this right here. I'm going to change this up like that. Okay, let's run this. This one will work. This better work. Oh, you know what? No. There we go. There we go. I don't know what I did wrong. Okay, so now I have my charge. I have my dielectric as a bunch of points right there. I'm going to go ahead and add those points to a list so I can use it to calculate electric fields and stuff like that. So let's go back over here. I'm going to say P. I'm going to call them P's. It's a list of dipole moments, P's. It's an empty list right there. And then what I'm going to do is to add that here. P's equals P's plus that list. Let's make the radius a little bit smaller. It doesn't really matter. I can make them 0. And I'm going to give them another property called P. And P is the dipole moment of that particular point. So P is going to be equal to, start off as vector 0, 0, 0. But then I can change it. Okay, let's just run it to make sure that that did indeed work. And it didn't. Missing a right bracket. Oh, okay, I did miss that. Let's see, where is that? P's down here. No, bracket. Okay, run it. I'm going to give you the code, don't worry. Okay, so there's all my points. Good, nice. Now what I want to do is to calculate the dipole moment at each one of those places. I'm going to use the dipole moment instead of the polarization because the polarization is the dipole moment per unit volume. So with that, what I'm going to do is to define the polarizability of each atom alpha. So let's say alpha is 0.01. This is not a good number, but we're just doing an exercise here. So for P in PS, I'm going to go through each one. I'm going to calculate the electric field at that location, which I need to do now, and then I'm going to use that to calculate the dipole moment. So let's just first of all calculate this vector. I'm going to call it RT. It's going to be the vector from my charge. It's just going to be the location of the dipole moment because my charge is at the origin. This is a shortcut. Shouldn't do this. Going to do it anyway. So it's just going to be P.POS. That's the vector. Now I can calculate the electric field. I'm going to call this E1 just because it's that charge E1. And it's going to be equal to, I'm using epsilon naught here. So it's going to be 1 divided by 4 times pi times epsilon 0. I put that number, and I put epsilon naught as 1 just to make things easier. So that's my constant K times Q1 dot Q is the charge of that one. I put it as a property, right? Yep, which is 1. Times norm RT divided by mag RT squared. So that's just the electric field due to a point charge. Now I can set my dipole moment. So P dot P, the dipole moment of the P element, is going to be alpha times E1. Okay. Now I'm also going to draw an arrow at that location. So up here, let's call another variable called P scale. I'm going to set it equal to 1. So I'm going to make an arrow there. Arrow, I'm not going to give it a name or anything. The position is going to be equal to P.POS. The axis is going to be equal to P scale times P.P. And the color is going to be yellow. That's the dipole moments. So let's just see if this calculates the dipole moments for all my points in my dielectric. There they are. It actually worked out pretty well. Okay. So now I have dipole moments for each one. Okay. Now we are set. The next thing I'm going to do is I'm going to calculate the flux, right? So in order to calculate the flux, I need to calculate the electric field. So let's do that. To calculate the electric field, I'm going to make a function. So I'm going to call a function def. I want it up here. Def, I'm just going to call it E. And I'm going to give it some vector location where I want to calculate the electric field. And then I'm going to use all of the stuff that I have to calculate that electric field. So I'm going to start off with ET, the temporary electric field, is the electric field due to that point charge. So it's going to be equal to 1 divided by 4 times pi times epsilon naught times Q1 dot Q times norm ROT divided by mag ROT squared. Just the electric field due to point charge. Now I need to go through and find the electric field due to each one of those dipoles. Now I didn't write it on the board, but we know how to calculate the electric field due to a dipole. So I'm going to say ET is going to be equal to ET plus, right, I'm going to add, I need to do this. 4P in PS. So I'm using that list of things. And then I'm going to add this. So the electric field due to each dipole is going to be equal to 3 times, this is kind of dumb, dot P, and then the vector, let's call this vector RT is going to be P.POS. P.P norm RT times norm RT minus P dot P. All of that divided by 4 times pi times epsilon 0 times norm RT, no, mag RT cubed. So that's the electric field due to a dipole. So I'm adding that to the total. And I go through every single one, and then I'm going to do that. And then when I'm done, I return ET. Let's just try and see if it works. So I'm going to print, let's say RO is the vector 2 times L 0, 0, and then I'm going to print E of RO. I just want to see if the function works. Because I make mistakes sometimes. I don't know about you, but sometimes I make mistakes. That one time I made a mistake. Remember that one time? Okay. I don't know if that's right or not, but it seems like it could be correct. Yeah, it has an X. Okay. I think that's right. It seems legit. Close enough. Okay. So now what we need to do is to create a sphere around the whole thing to calculate the flux. I did this before, and I have this program. I'm going to switch over to the other program right here, and I'm going to run it, and then I'm going to copy stuff out of there because I don't want to retype it. So this calculates the flux over some sphere. And I have inside of here do I have a dipole? Let's see what's inside. I think I have water. No, it's just a dipole. There's the dipole. And you see this is a zero flux situation because the total charge inside is 0, but the flux is not uniform. And it looks cool. So here I have, I break the surface of the sphere into smaller circles, and then I use a bunch of stuff just to find that. I made a video on this. If you can't find this video, just let me know. So what I want to do is, I'm trying to see what parts I need to copy. I need this stuff. Theta, phi, d theta, d phi. I need the area. I need all that. So let's copy that. Put it down here. And then I need, those are the charges I used before. I have my own electric field. This creates all those things right there. Switch over here. Paste that. That's a double loop over the surface area. Yep. Okay, and then this calculates the electric flux. Now I might have to change something here, but I'm just going to, let's just copy all this. I think I got it. E-scale, I don't actually need that, but let's just try it. Okay. It might work. ED. Oh no, this is wrong. ED is just going to be the electric field. So it's just going to be E A dot POS. I think. ED. I think I'm going to run it and let's see. I think it might just work. Let's just see. Okay. It may have in fact worked, and in fact it did. I can't believe it. So now this, it should not be negative right there though. Maybe it should be. I think my dipole moment here is too great, and that's fine. So these dipoles are too big. And that's making this whole thing act like a positive and negative giant dipole. My dipoles are more important than my individual charge. Let's fix that. Let's make alpha much smaller up here. Okay, oh, it's still positive. Okay, let's see what I did here, because I want to see where I have the blue and the red. So if phi, d phi, so d phi is E dot, that's fine. Oh, ED. Oh, ED is E. So some of those should be positive and negative. They should all just be positive. Okay. I'm gonna leave it here. I think it is okay. I think what the problem is that I'm still having that dipole moment for my induced thing is just too massive, and it's overwhelming the charge. It's not realistic. It's just too massive. I have too many point charges there. But the point is, when I run this, my flux is 1, right? So I have Q over epsilon naught. Q is 1, epsilon naught's 1, so I should get the same flux of 1. That's what I want. That's what I get. So you don't have a uniform flux. You don't have a uniform electric field, but still Gauss's law works. If I integrate over that surface, I still get 1. And that's the important point. Okay, so if I have a simple situation with spherical symmetry, yes, that's what I get. I can use it and it all works. It still works in other cases, it's just not useful. Link to this code down below. I'm going to make another video about dielectrics, a couple more. The end.